Welcome. This is a time series analysis course. My name is Nigarda Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is a multivariate time series analysis with a focus on data examples using the R statistical software. And in this last lesson, I will finalize the analysis on river flow data with an analysis using multivariate time series modeling. In this study, we'll forecast again the flow of the Chattahoochee River. We'll begin with a classic VAR model applied to the trivariate time series, including log transformation of river flow, temperature, and rainfall. As before, we first select the order for the VAR model, which is p equal to 1 for this data. When fitting the VAR model, we consider a seasonal deterministic component specified as season equal to 12, and we assume a trend specified as type equal to both, which means fitting both a constant and a linear trend. We can also further reduce the model using the var restrict R command. We'll next look at the outputs for the river flow for both the var and var restrict. This is the output from the VAR model for modeling the river flow time series. The first three rows in the output matrix of the estimates are for the coefficients for the lag t-1 time series. The next coefficients are for the constant and for the trend. And the last 11 coefficients are for modeling seasonality. Note that we only have 11 coefficients for seasonality while we are modeling monthly seasonality, and hence we should instead have 12 coefficients. Similar to modeling seasonality using dummy variables as introduced in the first lecture of this class, we only include 11 of the 12 dummy variables because the dummy variables are linearly dependent, and since we with the column of ones, and since we include a constant or the intercept, we only include 11 of the dummy variables. What can we learn from this output? First, the coefficients for lagged river flow and rain are statistically significant. Second, the coefficient corresponding to trend is not statistically significant, given that all other factors, modeling seasonality and zero correlation, are included in the model. Among the seasonality dummy variables, some of the coefficients are statistically significant, some are not. The R-square of the model is about 0.57, or if we would use interpretation from linear regression analysis, 57% of the variability in the response is explained by the predicting variable included in the model. This is the output from the restricted VAR model for modeling river flow time series. To note that the restricted VAR simply drops those coefficients which are not statistically significant, which is not the correct approach to do model selection, since as we learn in regression analysis, when removing one predicting variable, the statistical significance can be very different from the model including the predicting variable. To understand this concept, I recommend learning about variable selection from the online regression analysis course. Based on this output, we can see that the R-square has increased significantly to 90%. This is much higher than the full model. Does the temperature and rainfall grandeur cause river flow? Here is the output performing the wall test for the null hypothesis that all coefficients corresponding to the lag t-1 of the two time series are 0. Based on this test, the p-value is small, hence we reject the null hypothesis. This test says that at least one of the time series grandeur causes river flow. Let's compare the predictions based on the VAR and restricted VAR models versus the observed time series for 2016 and the first 3 months of 2017, hence predicting 15 lags ahead. This time, I'm using the predict R command instead of forecast R command to show you a different implementation of the prediction. First, we consider the predictions only for the river flow, hence the $sign followed by the name of the time series. To know that the predict will provide predictions for each of the 3 time series, but we are only interested in the predictions of the river flow. Also note that the output of the predicted R command is a list, and only the first element in the list provides the predictions. The object called pred in this slide provides not only point predictions or forecasts, but also the prediction intervals for the predictions. We apply this implementation for both models. Here are the predictions and the prediction intervals. The points in red and green are the point predictions from the two models, and the dotted lines in red and blue are the prediction bands. Both models perform similarly. The point predictions are quite different from the observed data. More importantly, the observed data fall outside of the prediction interval. In fact, they underpredict and pointing to poor prediction overall. Next, I will illustrate the implementation of the var-X model, in which I fit a var model to the bivariate time series including log transformation of the river flow and rainfall, while temperature is now an exogenous factor. This implementation is used only to illustrate the var-X model. The implementation using the var-R command with similar input as before, except that this time I'm including another option in the var function specifying the exogen equal to temperature. The rest of the implementation is just like the var model without exogenous variables. This is the output of the var-X model which includes temperature as an exogenous variable. The regression coefficient for temperature as an exogenous variable is not statistically significant, given that we accounted for seasonality, trend, and zero correlation in the river flow modeling. Importantly, the estimated coefficients based on this model are similar to those from the model where temperature is an endogenous variable. In this slide, I'm comparing the prediction of log river flow based on the three models, var, ARIMA, and ARIMA-X. ARIMA-X and var perform similarly because ARIMA-X accounts for lag relationships at temperature and rainfall. ARIMA does not predict worse than var or ARIMA-X, but it does have more uncertainty, where the prediction band includes the observed values and hence better predictions. In summary, I concluded the analysis on river flow data with the modeling using multivariate time series, and I compared the forecasts based on univariate and multivariate time series models. Thank you.